Each year, the world invests over $20 billion in what appears to be nothing more than sculpted metal. But these are magnets, the silent hearts beating within every motor, turbine, and modern device. Their simple appearance belies a sophisticated fusion of material science, metallurgical engineering, and precision on an atomic scale. The journey begins with rare earth ores extracted from deep underground. From there, humanity orchestrates dozens of complex stages, including purification, melting, the pressing of fine powders, sintering, and the final act of magnetization. It is here that inert metals are transformed into an invisible power, a force that now serves as the foundation for our technological future. The modern world turns on a hidden axis of power, a power measured not in armies, but in elements. Today, the global stage for rare earth magnets is shaped by one nation, with China commanding more than 90% of the world's refining and manufacturing capacity. From the sprawling neodymium mining operations in Inner Mongolia to the humming sintering plants along its eastern coast, nearly the entire supply chain for magnet production is held firmly within its control. Beginning in the year 2025, a new export regulation is set to tighten this grip. The policy mandates that any product containing even the smallest fraction of Chinese-sourced rare earth material must first secure official approval before it can be shipped abroad. This directive has forced many Western corporations into a state of reliance on Chinese authorization, igniting concerns over a potential strategic chokehold on the high-tech supply chain. With such comprehensive dominion over this foundational sector, a stark question looms large. What would become of electric vehicles, of wind turbines, and of American manufacturing itself if the flow of these critical magnets were to suddenly cease? They begin as humble stones locked away in the dark. Yet within them sleeps the power to move our modern world. The journey starts deep underground, where veins of rare earth ore, rich in elements like iron, barium, or strontium, are threaded through ancient rock. Geological engineers meticulously survey these deposits, drilling exploratory holes to pinpoint the most potent zones of neodymium and other prized minerals. To liberate the ore from its rocky prison, they rely on carefully calculated blasting, placing explosives with surgical precision. This ensures the ore breaks away in intact blocks, preventing fragmentation that could compromise the quality of the rare earth elements inside. Unlike the brute force of large-scale iron mining, this extraction is a delicate art, demanding absolute control. Once the dust settles, heavy conveyor belts and specialized trucks carry the liberated ore blocks to collection yards. Here, they are sorted into distinct piles based on their composition, ready for the next phase of their transformation. Throughout this process, a hidden danger lurks, since rare earth ores can contain traces of uranium or thorium. Dust and toxic gases are strictly monitored and minimized to protect every worker on site. After arriving at the factory, the raw ore blocks undergo a preliminary cleaning to wash away clay and surface impurities. The cleansed ore then moves to the milling section, where it is fed into the powerful jaws of a ball mill or a jet mill. For several hours, the material is pulverized into a fine powder. The rotation of the grinding drum is held steady between 20 and 30 revolutions per minute, while the compressed air in a jet mill is maintained at 85 to 100 pounds per square inch. This grinding continues for 4 to 6 hours, reducing the particles to an average size of just 3 to 10 microns. To preserve their natural magnetic properties and prevent any alteration to their crystal structure, the temperature inside the grinding chamber must never rise above 180 degrees Fahrenheit. Once the process is complete, the resulting powder is cooled with inert gas and passed through a multi-layer screening system, which carefully separates the particles by size. From here, the fine powder enters a flotation tank, where valuable rare earth particles are separated from worthless rock and sand. The powder is mixed with water and special chemical reagents, creating a churning liquid emulsion. As air is pumped through the mixture, the desired elements, neodymium, samarium, and iron oxide, cling to the rising bubbles and float to the surface as a purified froth. Heavier impurities simply sink to the bottom, left behind. This is a process of extreme precision. Unlike the flotation of common metal ores, Rare earth elements exist in very low concentrations and are easily contaminated, requiring meticulous control over both the froth and the slurry. The entire operation unfolds inside a sealed tank, equipped with dust collectors and chemical control systems to capture any harmful substances released from the ore. Each batch lasts from 1 to 2 hours, giving the valuable particles just enough time to ascend and be collected. With the purified powders collected, engineers prepare the raw materials for alloy production. They first examine each batch for purity, moisture content, and elemental ratios, ensuring everything meets exacting standards. For rare earth magnets, they combine neodymium, iron, and boron in precise proportions, while ferrite magnets require a mixture of iron oxide powder with barium or strontium. Every ingredient is weighed with absolute accuracy, a critical step that guarantees the finished magnet will possess a strong and stable magnetic field. Once mixed, the materials are immediately transferred into sealed containers, shielded from air and any potential contamination. An element so reactive it must be born in a void. To guard against contamination from the air, the process begins inside a chamber, purged of all oxygen and moisture, then suffused with inert argon gas. This environment is critical as it prevents the oxidation that would otherwise destroy neodymium, a metal acutely sensitive to air. Once the raw materials are inspected and combined, they are charged into an induction furnace. The temperature inside climbs to a staggering 2,500 to 3,000 degrees Fahrenheit. For the next 2 to 4 hours, the mixture is heated continuously, allowing the neodymium, iron, and boron to completely liquefy and blend into a uniform alloy. This duration is precisely calculated to forge an ideal crystalline structure while preserving the integrity of the rare earth elements. With the metals now fully molten, the alloy is quenched in an instant. It cascades onto a rapidly rotating drum where the liquid metal solidifies into thin metallic flakes within a few seconds. This technique of instantaneous cooling freezes the material into a fine and uniform crystal structure. From here, the refined alloy is pulverized into an ultrafine powder inside another inert gas environment, once again shielding it from oxidation. The resulting substance is a dark gray mixture with a subtle violet tint, its particles measuring only a few microns across. This magnetic powder is then fed into a high-pressure steel mold and simultaneously exposed to a powerful magnetic field reaching several Teslas. Within this intense field, millions of microscopic alloy particles begin to rotate and snap into alignment, all pointing in the same magnetic direction, much like countless compass needles orienting toward a single pole. The entire alignment unfolds in mere dozens of seconds, yet it demands absolute control over pressure, magnetic intensity, and compression speed. Any inconsistency could shatter the crystalline alignment, preventing the magnet from ever reaching its full potential. The outcome is a set of solid yet brittle alloy blocks, whose crystal structure has been perfectly oriented. These are the magnetic blanks, poised for the heat treatment that will unlock their final power. Though they appear solid, these freshly pressed blocks are as fragile as ceramics and possess no magnetic properties yet. To transform them into true magnets, they are placed inside a sealed furnace, completely isolated from the outside world. Inside this chamber, the temperature gradually rises to about 2,200 to 2,400 degrees Fahrenheit. This is just hot enough for the surfaces of the powder particles to soften, allowing them to fuse and bond together under the metal's own weight. For the next 4 to 5 hours, the system maintains this stable temperature, enabling the alloy particles to compact tightly and eliminate even the most microscopic voids between them. During this phase, the material transitions from a porous form into a fully dense solid, achieving nearly 100% of its bulk metal density. Once this equilibrium is reached, the temperature is slowly reduced over several hours, degree by degree. This deliberate cooling gives the crystal structure time to lock in the previously aligned magnetic orientation. Finally, an additional heat treatment at around 950 degrees Fahrenheit stabilizes the entire structure, completing the sintering process. After the center blocks have hardened into solid forms, they move on to machining and protective coating. At this stage, the magnet blocks are cut, ground, and drilled using precision tools like diamond blades or laser systems, sculpting them into the exact shapes and dimensions required by their design. Next, the magnets receive a protective coating that guards against corrosion, moisture, and mechanical wear. For these neodymium iron boron magnets, the coating typically consists of nickel, zinc, or epoxy, which not only shields the surface, but also preserves the internal magnetic strength. This protective layer is not an option, but a necessity, as without it, the magnet's force can degrade rapidly, compromising both performance and longevity. Once machined and coated, the magnets remain completely dormant, showing no north or south poles. The magnetization stage is the process that awakens their true power. Each magnet is placed between the poles of a pulse magnetizer, where an extremely high electrical current, reaching between 2,000 and 3,000 volts, is discharged in just 1 to 5 milliseconds. This surge generates an instantaneous magnetic field with an intensity of about 5 Teslas, tens of thousands of times stronger than the Earth's own field. In that brief, violent moment, all the magnetic domains inside the alloy align perfectly in the direction established during molding. This synchronization allows the magnet to achieve its maximum remanence, BR, and coercivity, HC. If the magnetic pulse is too strong, internal stress can distort the crystal structure. If too weak, some domains will remain disordered, causing a noticeable drop in magnetic strength. After magnetization, each magnet's surface field is measured with a Hall sensor, and its polarity is verified by an automatic orientation tester. Those that fail are demagnetized and reprocessed, while the qualified ones are prepared for final inspection. Following magnetization, every magnet undergoes rigorous quality inspection before shipment. Each piece is tested for magnetic strength, pole orientation, thermal resistance, and corrosion protection to ensure it meets both technical standards and customer requirements. Specialized instruments allow engineers to immediately detect any magnets with uneven force or incorrect pole alignment. Next, the magnets are packaged with extreme care. As their pull is immensely powerful, each piece is separated by non-magnetic shields or special plastic spacers to prevent them from snapping together or damaging their surfaces. The storage boxes are engineered to withstand impacts during transport, ensuring the products arrive at motor factories, wind turbine manufacturers, and robotics plants in perfect condition. This packaging also contains their magnetic fields, preventing interference with nearby electronics and ensuring each magnet retains its full strength. Once inspection and packaging are complete, the finished products are ready to power modern technology, where every magnet becomes an invisible yet formidable force driving entire systems. Once forged, their power is unleashed, driving entire systems from within. The invisible force contained in these magnets begins to fuel a vast array of modern devices and technologies, shaping the world in ways we rarely see. In the electric vehicle industry, neodymium iron boron magnets are installed deep inside motor rotors. There, they generate a formidable magnetic field, enabling fluid operation, improved energy efficiency, and the highest levels of performance. Within towering wind turbines, precisely oriented magnets are arranged inside the rotor to convert the motion of the wind into electricity. This efficient process helps deliver clean power to millions of homes. These magnets also serve as the beating heart of industrial robots and medical equipment. Their powerful magnetic fields ensure unwavering precision, guiding everything from robotic arms assembling cars to the magnetic resonance imaging machines that scan the human body. Even in the everyday electronics we hold in our hands, their role is crucial. From speakers and hard drives to the tiny sensors inside smartphones and computers, these magnets are vital for generating fields, converting energy, and directing signals with incredible accuracy. They are fragments of metal small enough to hold in your hand, yet their silent force moves the very foundations of our world. This remarkable journey begins deep within the planet's crust, where raw ore is unearthed, and concludes with these unassuming objects that silently power our modern lives. Each small piece of metal carries an invisible strength, a force that animates the technologies shaping our existence. This unseen energy turns the rotors of electric motors and drives the colossal blades of wind turbines against the sky. From extraction and grinding, to molding, centering, and machining, through the final acts of magnetizing and quality testing, Every stage is a testament to meticulous control. The entire process is guided by human ingenuity, a quiet reminder that from the humblest of materials, we can forge components that hold extraordinary power.